Okay, so let's probably start. So I just want to make a quick few announcements. So first of all, thank you for providing all this midterm feedback. This is super helpful. Tia and I, we will basically go through every of the comments and try to make adjustment in the next in the next half of the semester. Right. So the first announcement is that homework 2 will be out this Friday, sometime Friday night. So you will basically try to do some math problems on policy gradient, and then do a programming problem. Again, on this couple simple example, but you will implement some policy gradient algorithm and then try to see, how policy gradient actually making progress constantly. Right. And another thing that I want to say is that starting from next week, I'm just going to add additional office hour every Monday from 11 a.m. to noon. So that now, we have office hour every day throughout the whole week, right? So in case you need help on homework or, you have questions about the course material, just feel free to come to this additional office hour. Right? Any questions so far? All right, great. Okay, so let's jump into today's material. So let's just do a quick recap on policy gradient. Right, so we have this objective function in hand, right? So we have a parameterized policy pi theta, where the parameter is denoted as theta. And what we talked about in the previous lecture is that we can derive this policy gradient formulation for this objective function, right? So our objective function is a function with respect to the parameter theta, and we can just compute the gradient with respect to that objective function, right? And with that, we can just do, usual gradient ascent. So in our case, we will sample state action pairs to replace this expectation, right? And with that, we can just do stochastic gradient ascent. And the usual proof for stochastic gradient ascent will just be, you can just directly apply it here. Right? So the idea behind this formulation is that, we want to incrementally adjust our parameter such that every iteration, this new policy will gradually increase the probability of sampling an action whose advantage is large at this moment, right? And simultaneously downgrade the probability of sampling an action whose advantage is actually negative at this moment. Right, so that is policy gradient. At this stage, this algorithm, so if you just take this formulation and you replace this policy pi theta by a deep neural network, right? So this is pretty much, the state-of-the-art algorithm people use in practice. Like, one nice thing of this policy gradient formulation is that literally you can use any differentiable function to represent your policy, right? As long as you can compute the gradient. So you can just parameterize your policy by a neural network that takes state as input and outputs a distribution over action, and then take log on top of it and just ask these order differentiation tools to do backpropagation on this function, and then you get a gradient, and then you just plug it into this formulation and you can do stochastic gradient ascent. Right. So this is one of the major advantage of policy gradient, because you can use very complicated as long as it's non-differentiable, very complicated function as a policy, and as long as it's differentiable. All right, so let's also do a quick recap on this conservative policy iteration. All right, so this conservative policy iteration says that every iteration, I have the current policy pi t in hand, and let me first compute the most greedy policy that maximizes the local advantage, right? The advantage against the current policy averaged over the current policy state distribution. Right, we talked about how to do that to use a regression oracle. Right, but then we talked about this approximate policy iteration algorithm. So if in the next round we just commit to this most greedy policy, this pi prime, we will never guarantee that we will have monotonic improvement. right? So that's what we talked about. And what CPI does is that let's try to make incremental updates in the sense that I'm not going to commit to pi prime in the next round. All I'm going to do is actually just move towards that pi prime a little bit. Right? So that is the CPI algorithm. And in the class, we asked these two questions, right? So why this is incremental, in what sense? And can we get a monotonic policy improvement? Right? So the answer to the first question is yes. If you make a small update, if we just move a little bit towards pi prime, the greedy policy, we can ensure that this new policy's state distribution and the older policy's state distribution under this L1 distance measure, they're bounded, they're small. Right? The smaller the step size is, the smaller this distribution difference is. Right? And then we also showed that this actually guarantees monotonic improvement, right? As long as the algorithm does not terminate. As long as the algorithm can still find, a locally improvement, a policy that has local improvement. All right, so, some of you also asked the questions in the class that, how can we actually implement this algorithm, right? So I guess for the pros and cons of this algorithm, so the pros is basically this is a very fundamental, right? The idea of incremental update and the theorem behind it is actually super fundamental. Everyone's still using that even in today's research, right? Like even today's papers, they're still using these ideas like incremental policy update and the theorem of performance difference lemma, for instance. Right, and the cons is definitely very obvious. There's some practical issue, right? Like the memory issue. So what if my policy is an extremely large neural network? Am I going to store all the policies in my computer? Right, that seems a little bit unrealistic, right? So that leads us to today's question. So can we develop some practical version of conservative policy duration? All right, so instead of storing many policies, can we just keep updating one policy, right? Particularly, can we just use parameterized differentiable policy, right? So that we just needed to update our parameters rather than store all the previous policies that we have seen so far. Right, so we're really going to talk about an algorithm that is practical and also gives really good performance as well. So this is pretty much one of the state-of-the-art algorithm people use today. And this is the algorithm that you're going to implement for homework 2. All right, so a quick outlines for today. So we're going to do a quick intro to this KO divergence. So some of you probably heard of it. So this is the divergence that measures the difference between two distributions. All right, and then we're going to do a trust region formulation for policy optimization. So basically, we're going to write down a formulation, says that let's find a policy that maximizes the local advantage subject to a trust region constraint, in the sense that the new policy has to stay close to the current or older policy. Right? And then we're going to put everything together to get to this algorithm called natural policy gradient. So that's the plans for today. Right? Any questions so far? Okay, great. So let's take a look at an example. All right, so let's see, what I want to train a robot to run forward as fast as possible. Right? The reason that I put this code on the word run, you will see the reason in a second. So here the state is the joint angles and center of mass, velocities, and so on and so forth, right? Basically, this information that describes the current state of the robot. And the action is the torques on joints. Right? And the reward function is that, so since we want to design the robot to run forward as fast as possible, I'm going to design a reward function that is basically proportional to the distance of moving forward between two steps. Right? I take an action, I observe where the next position of the robot is. I'm just going to give it a huge reward if the robot moves forward, right? And a small reward if it only moves a little bit forward. Right? So that sounds reasonable. And I can use policy gradient algorithm that we talked about with neural network parameterization. And we can also use the algorithm that we're going to talk about today again, with neural network parameterization to train this task. So let me show you some interesting videos. All right, so this is the robot that we want to control. And this is the outcome of the policy that we learned. Right, so the robot is definitely moving forward, but it's not running. Right, but in terms of optimizing the reward function, it's actually doing a reasonably good job because it's constantly moving forward and it gets tons of reward. Right, let's look at another example. So the robot is actually doing this backward walking or running. This is another, the sort of the policy that will be optimized by this policy gradient or the algorithm that we're going to talk about today, right? So in other words, the algorithm is doing its job. It's doing gradient descent, and it's doing gradient ascent, and then it converges to a solution that actually gives you this behavior, right? If you start from different random initialization, you get to different solutions, right? And in terms of maximizing the reward, yes, it's doing its job, right? Because it's moving the robot forward. And lastly, you could also get into this kind of situation. The robot is actually running forward pretty fast, but it has weird behavior on its arms and so on and so forth, right? And again, this is a potential outcome, a potential converged solution from this gradient descent algorithm, right? So in other words, this gradient ascent algorithm, it's just optimizing the objective function, right? But it potentially could lead to different kind of local optimal solutions that gives you this weird behaviors. But they are all, optimizing the reward function that you give. Right. So these are just some interesting videos, for training this humanoid robot to move forward as fast as possible. All right. So this actually reviews an issue on the reward design. Right. Remember, as a if we design a reinforcement learning algorithm, if we're trying to apply reinforcement learning algorithm on some our application, we have to design the reward function, right? So this actually reviews the issue of reward design. We will actually study how to do reward design more properly when we get to this topic on learning from demonstrations. All right, so that's just the examples that I want to show. So now I'm going to just switch to my iPad. Okay, any questions so far? Okay, great. So let's just jump into the KO divergence. Okay, so this is the video that we just saw. Yeah, I mean, one of the motivations that I showed this video is that these algorithms, they're really effective in terms of aggressively maximizing the reward of function, the objective function you designed, right? Because they're doing gradient descent, they're doing gradient ascent, and they're doing constant improvement on the objective function, right? So they're pretty effective, and even for controlling this complicated 300-dimensional humanoid robot, right? Okay, so let's talk about KO divergence. So KO divergence is a measure that measures the distance between two distributions, how different two distributions are, right? So this is the definition of KO divergence. So if I have two distributions, P and Q, right, the KO divergence is defined as the expectation under the first distribution. And then inside the distribution, it is the log of the ratio between P. If it is the log of the ratio of P over Q. Right, so in order to understand this, let's just take a look at some examples of KO divergence. Right, so the first example is that what if P equal to Q? In the sense that Px equals to Qx for all x. Right, so this is obvious that the KO divergence will be 0, right? And regardless of what the order you use, whether or not you use KLP in front or Q in front, it doesn't really matter. So if you just plug it in, it just gives you 0, right? Because log of 1 is 0. So this measure makes sense because if the two distributions are the same, their divergence should be 0. Right? Let's look at a more concrete example. So let's see my P is a Gaussian distribution with mean mu1 and covariance matrix sigma squared times identity. And let's see our distribution Q is another Gaussian distribution with a different mean mu2, right? But the same covariance matrix sigma squared identity. And we can actually literally plug in the Gaussian distribution formulation into the KO divergence and simplify the expression, and we will get to this pretty simple expression. So that basically says that the KO divergence between two Gaussian distribution with the same covariance matrix is the L2 norm, the square of the L2 norm between the two means, properly scaled by their variance, sigma squared. Right? Again, if the two distributions are close to each other in terms of their mean, then this scale divergence is small. Right? If the two distributions are really far away from each other, the scale divergence is big. Right? So in this example, you can also see that KO divergence actually will be infinite. So imagine two Gaussian distribution whose mean, are infinitely away from each other. So then the KO divergence could be infinite. Right? It's not bounded. Yes, I see there's a hand raised.
So in general, KL divergence won't be symmetric, right?
Yeah, it's not. Yeah.
Okay.
So this is a very good question. So still KO is not symmetric in the sense that KL of PQ does not equals to KL of QP. Right? So one good example that you can actually check offline is that try to compute the KO divergence between two general Gaussian distribution that also have different covariance matrix. You will see that they are different. If you do KO of PQ and KO of QP, they will be different. Right? Right. And there are also some interesting fact. So KL is always non-negative. Right? That totally makes sense from the divergence perspective, right? Like a negative divergence, I don't even know what it really means, right? Like divergence should always be non-negative. And this KL is 0 if and only if P equal to Q. Right. So, I mean, this KL divergence looks like a good distance metric, except that it's not symmetric, right? Other than that, everything makes sense. When P and Q are close to each other, KO is small, and KO is equal to 0 if and only if P and Q are exactly the same.
What if P is repeatedly smaller than Q, and then in some case it's larger, but in a lot of cases it's less? Like, let's say P is like 0.01 for a whole bunch of x's, and Q is, well, oh, I see, because it's a problem. Okay, never mind.
Yeah, though that's not going to happen, right? Because integral of Px equal to 1, right? Integral x of Qx equal to 1. Right.
So actually, I had a quick question. I'm just curious, like, what is the reasoning behind defining KL divergence in this way? Like, why take the natural logarithm of P divided by Q? Like, could you come up with other types of divergence that have the same properties, right?
Yeah.
Like, what's the intuition?
Totally. So this is related to sort of the information theoretical quantity called entropy. Okay. Right. So maybe we just spend 1 minute talking about entropy. So if I distribution P, so entropy is defined as the expectation of x from P of negative of log of P x.
Right.
Or let's do log base 2. Right. So this is essentially saying that, like, in expectation, how many bits do I need to use to sort of encode this distribution? Right. That's why I'm using log 2 base. But log E and log 2, they're basically different. Like, it's a constant difference, right? So, and the KO divergence is in some sense saying that if I encode the because you can really think about this as the entropy log of px minus expectation of x over p log of qx. Right. So the first term is sort of expressing, how many in expectation, how many bits do I need for expressing this distribution p. And the second one is kind of saying that if I mistakenly believe that my distribution is p, but I'm sort of trying to deliver a message, like encode a distribution using q, what's the expected bits that I need, right? So this scale divergence is sometimes measuring the difference between these expected bits that you need to use.
I see. So like you assume you have a probability distribution Q, and based off of that probability distribution, how many bits do you need to encode the outcome? Okay, I see.
Yeah, so this is the entropy. And you're right, like you can design divergence that looks like this. Where f is some monotonic increasing function. Right, so this is called f divergence. So if you heard about this generative adversarial net, it uses one of the f divergence. So basically a particular formulation of f. Right. So one interesting thing is that we can show that we can upper bound the total variation distance using the KO divergence. So that is always true. Okay, so this is just another fact. So we're not going to prove that. Okay, so that's basically the 1 minute quick intro of KO divergence. Right, so you just think about this as a measure between a divergence measure between two distributions. Right, quantifies how far away these two distributions are with each other. Okay, so now let's jump into the second part of this lecture. So let's talk about a trust region formulation for policy optimization. Right, we're going to use a KO divergence to define a trust region constraint. So first, a quick recap on the policy parameterization. Right, so again, here we are talking about parameterized policy pi. So again, the first example, think about this as a logistic regression, linear logistic regression, right, for multi-class classification. And the second one is multi-class classification using neural network parameterization. Okay, so each policy pi is just a classifier that has its own parameters to be optimized, right? And they're differentiable. Okay, so a trust region formulation is, so we're going to talk about this in the iterative policy optimization framework. So let's see at iteration t, we have this pi theta t at hand that we computed from the previous iteration, for instance, right? So we now going to update theta t to theta t plus 1 using the following optimization program. Right? So let's look at the objective function. So the objective function is essentially similar to the greedy policy selector, right? So this basically says that I want to maximize a policy pi theta such that it achieves the maximum local advantage against the previous policy pi theta t, right? So here I'm averaging state over pi theta t, and the advantage is defined with respect to the previous policy pi theta t as well. And I'm trying to find the action that maximizes the advantage, right? So this is exactly the greedy policy selection step in CPI. Right? Ignoring the constraint for now, this objective function says, let's be greedy with respect to the current policy. Right? Let's find the one that maximizes the local advantage. Okay, but we know that this is a terrible idea from the approximated policy iteration lecture, right? The policy is going to oscillate between two policies and never going to make any improvement. And the CPI tells us that you have to be incremental. You have to make sure the new policy is not that far away from the previous policy. All right, and that motivates us to introduce this KL trust region constraint. All right, so this KL says that I want to make sure that the trajectory distribution of my new policy is not too far away from the trajectory distribution of my current policy under the KL divergence measure. Right? Let me remind you that this is the trajectory distribution. Right, so a rho tau is pi tau is mu S0 pi A0 S0 P S1 0 A0 so on and so forth. Right, so very similar to the CPI concept. It's just basically saying that let me just be greedy with respect to the advantage, the older policy, but let's just put a harder constraint on this optimization program, right? Let's make sure that the new policy is never going to be far away from the older one in terms of KO divergence between the induced trajectory distribution. All right, and this is the hyperparameter that you're going to tune. And this constraint is what I called trust region. Right, so if you think about KO as maybe an ellipsoid, so you have rho pi theta t at the center, right? So this is like your radius delta. You want to make sure that you only do optimization inside this circle. Right? It's just that the distance metric in this circle is defined in terms of KO divergence. Okay. All right, so yeah, so in words, we want to maximize the local advantage against the older policy, but we want to make sure that the new policy is never going to be too far away from the current one, right? In the sense of KL. So now the key question is that how do we actually do the optimization here, right? And after all, we don't even know the analytical form of the trajectory likelihood. Okay, yeah. Question?
Is the reason we are looking at this defined trust region because we don't want the new policy that we get to, like, even if it does maximize his expectation, if it's too far away in the scale sense, and what's the danger?
Remember the lecture where we're talking about the picture that I showed you?
Oh, right.
The two policy will oscillate, right?
Yeah.
So
I see. Okay.
Right. Essentially, we want to ensure incrementalness here in the policy update again, right?
Yep. And so do we compute this maximization, this max, using gradient ascent again?
You can, but we're not going to do it here.
Okay.
Like we don't want to do like two loop iteration, like two loops, right? We don't want to do that. Yeah, I mean it's not that easy actually. So we don't even know these two we can't even write down this formulation, right? Like you can't even implement this likelihood because you don't know the transition and the initial, like you don't know the transition, right? So that's why I said you don't know the analytical trajectory likelihood, so you can't implement that, right? You can't just implement that in Python, for instance, right? Because you don't know the transition, right? Okay, so we will do simplification on these two objectives, the first objective and the second constraint, and we will get it to a pretty succinct policy update procedure. All right, so that's the goal of the rest of the lecture, right? So we want to simplify this. Simplify this. All right, so high-level strategy. This is very similar to the LQR, the nonlinear LQR, the nonlinear control idea that we talked about. So what I'm going to do here is linearize my objective function at the current point theta t. Right? And I'm going to quadratize. I don't know how to write quadratize. And I want to do second order Taylor expansion on this KL constraint. Right. The hope is that I get a linear objective function after first order Taylor approximation, and I get a quadratic constraint after the second order Taylor expansion. So now I'm going to get into a much easier problem, right? I have linear constraints on my parameter. I have linear objective on my parameter, and I have quadratic constraints on my this constraint programming problem, right? So linear objective convex quadratic constraint is a convex program, so I can actually get global optimal solution.
So this is different from the LQR, because in the LQR we had a quadratic objective, but the linear step, right?
Yeah, yeah.
And here it's flipped.
Yeah.
Okay.
But it's again, it will be a convex program problem, right?
Yeah. Yeah. Okay.
And it's actually more than convex. We can actually get the closed form solution after we do this simplification, right? It will get a very simple, nice expression for the parameter update afterwards. But we have to do some work to get, to get to that nice expression. All right, so let's just simplify the objective function, right? So this is our objective function. This is potentially nonlinear, non-convex, right? Because my pi theta could be super complicated. It could be like 10, 20 layer neural network, right? Who knows what that is, right? Okay, so let's just take a gradient with respect to this objective function, right? With respect to theta, and measure it under the current solution theta t. So what is the gradient of this guy? Right? Anyone want to try and give an answer?
The same thing we described before, right? Last lecture, like a gradient with respect to theta, ln pi theta s times this to the a by theta s comma a.
Correct. Yeah. So do a one step of importance weighting, right?
Yeah.
And use the chain rule. Right, so this is nothing but just the policy gradient. Right, so this is the advantage-based policy gradient formulation that we talked about previous lecture. Right, so in other words, after we do first order Taylor expansion, we get to this term, and then the second term, which is basically the inner product between the gradient and the difference between theta and theta t. So this is an inner product. Right, and this term is 0 because the advantage against like yourself is actually 0, right? Because we're measuring the advantage under its own policy by theta t. Like there's no advantage, right? Okay, so this gets to a very nice simple expression, which is essentially the inner product between the gradient and difference between this theta and theta t. Right? So let me just write this. Approximately equals to right? So that's pretty nice. We know how to compute the gradient, and especially we know how to compute the unbiased estimate of the gradient, right?
Sorry,
yeah.
Just a little confused. Why is this term not? Oh wait, because of the weighting of the gradient. Is that why it doesn't equal to 0? Like the second term.
The second term. This is a policy gradient. This is just the gradient.
Oh, that doesn't equal to 0 because you're weighting it by the.
Yeah. Okay, so objective function Taylor expansion on it is simple, gives us pretty nice formulation, right? And at this point, we know how to compute this guy, right? We know how to compute this using a finite number of samples. So we are good at the objective. All right, so now let's see how we can do similar things for the constraint, for the KO constraint. Right, so in high level, let's write down the KO constraint, right? So this is nothing but just a function with respect to the parameter theta, right? So let's just abstract this away by writing this, defining this as L theta, where theta is the parameter, right? I mean, this KO is nothing but just a function of theta, right? It takes the theta as input, the output, a number. Right, let's just do second order Taylor expansion of L theta at theta t. Right, so zeroth order term, first order term, and this is a Hessian. Right, and we ignore the high order terms. Right, so that's the high level idea. And the first simple fact is that L theta t is just 0, right? Because L theta t is actually just replacing theta by theta t, then you get two same distribution. And we know that KO divergence between two same distribution is 0. So this is nice. The first term is 0, it goes away. Right? Now, maybe a little bit surprising, what we're going to show is that the first order term is also 0. So what we're going to show is that this gradient is actually 0. Right? And then we're going to show that this formulation is a pretty nice formulation. So at the end of these two steps, we will basically get to this approximation. Okay, because the zeroth order term is always 0, because KO between two same distributions is 0. And then surprisingly, we're going to show that the gradient of the KO measured as theta t is also going to be 0. All right, so the zeroth order term, the first order term, they just go away. And what we left is this nice quadratic term. Right, so that's what we're going to do. All right, any questions so far before we jump into the details? All right, we're going to do a bunch of gradients computation in the next 2 slides. All right, that's the high level goal. And we're going to do some calculations, some gradient calculations. These are detailed steps, but let's try to make sure that we understand the big picture, right? We have this complicated KL defined over the trajectory distributions. Like we can even implement this KL in Python, in NumPy, right? Because we don't know the transition. So what we suggested is let's just simplify it by taking second order Taylor expansion on it. Right? And what we learned for now is that the zeroth order term is always equal to 0. And what we're about to show is that the first order term is always going to be 0 as well. And what we left is the second order term. All right, great. So let's talk about the first order term, right? So the claim is that the gradient of the KO divergence is 0 measured at theta t. So that's our goal. Right? So we're going to do it in 2 steps. The first step is let's change from trajectory distribution to state action average distribution. Right? Just start from definition. This is the definition of KO divergence. Right? So I'm taking expectation under the first distribution, and then I'm taking the log of the ratio between these 2 distributions, right? Okay, so great. So what is the trajectory likelihood, right? So this is mu0 over S0 pi theta A0 0 P1, right? And let's divide it. Rho pi theta t. Right, so this is pretty nice because I can now just cancel a bunch of terms. Because these two definitions, they share the same initial state distribution and they share the same transition, right? The only difference is the policies. So I just cancel these common terms. So now I arrived at this expression, right? And one more step is let's add log on this both sides. And this is sum over h equal to 0 to, sorry, my bad, this should be infinite. Right, I just add log on both sides. Yes, question?
So the denominator should not have pi of theta t, right? Shouldn't it be just pi of theta?
Yeah, correct, yeah. Of course. Otherwise, yeah, this is just going to be a constant one, yeah. Okay, great. And let's just push the expectation inside this summation. And now we just convert everything into the state action distribution. Right? Because once we put the expectation inside the summation, what we care is only a particular distribution over SH and AH, right? So we marginalize over the rest of the variables and only keep the distribution of SH and AH. Okay, so I realized that I actually made some mistake here. Apologize for that. I actually do want to do finite horizon here. So I just want to add H here. Okay, so let me just make a claim here. We're doing finite horizon setting. Okay, but the idea is that let's just write out the KO divergence expression. Let's use the fact that, two trajectory, like the ratio between two trajectory distribution, they share a lot of common terms, right? The transition and the initial distribution. So cancel them out and push the log inside, and you get a summation of a bunch of terms where each term is just the log of the ratio between two policies. Okay, so every step is equality. There's no, approximation whatsoever. All right, so now let's just take a gradient with respect to this new expression, right? Okay, so I'm just gonna push this gradient expression inside the expectation because the expectation has nothing to do with theta, right? So this is the only parameter where I'm going to take the gradient, right? So that gives me this expression. Right? Because log of pi theta t, pi theta, this is just log of pi theta t minus log of pi theta, right? So the first term is nothing to do with theta. So take a gradient of respect to this term, it's going to be 0, right? Because it does not depend on theta. So I only have this second term left here. Okay, so what I'm claiming now is that this is actually equal to 0. And we actually did similar calculation when we introduced the baseline in policy gradient. Okay, so I'm gonna give you a few seconds to sort of recall what we did when we do like the baseline calculation in policy gradient. All right, so what we're gonna do is just apply the chain rule here, right? So I just apply the chain rule here, so I get this expression. I get this expression. I apply the chain rule here. Okay, so that is great because these two terms can cancel, right? So now I get negative expectation of S, gradient theta, sum over A, pi theta t, AS. Okay, what is this guy? This is negative expectation of S, gradient theta times constant 1. This is 0. Just literally the same trick that we did for the proving, you know, a baseline, a state action independent baseline does not affect the policy gradient, right? So essentially do the chain rule, you know, cancel this two terms, right? And push the gradient expression outside of the summation. And then you realize that now you're just taking gradient on a constant term, 1, which is the gradient of a constant 0, right? So you get 0 expression. Okay. So in other words, we just proved that this fact, right? Everything is equality. There's no approximation, no inequality, whatever, right? So we just proved that the gradient of this KO divergence measured at the current solution theta t is actually equal to 0. Right? So there are some detailed steps that you need to convince yourself, you know, this is correct. But the high level picture is that gradient at theta t of the KO divergence is 0. Right? So let's just go to the Hessian. Right? Let's compute the Hessian of this KO divergence. Remember, I've already did the simplification where I've already changed from trajectory distribution to state action distribution. Right? Okay, so there are some tedious steps because we want to compute the second derivative, right? So let's just do it. And at the end of the day, we will see that this is a very simplified expression. There's a very simplified expression. All right, and again, I'm just going to take, you know, the second derivative on this expression, right? And again, you know, the expectation has nothing to do with theta, so I'm just going to push this nebula square inside this expectation, right? And inside the expectation, I have log of pi theta t minus log of pi theta. So the first term has nothing to do with theta, so it's 0 anyway. So all I'm left is just the second derivative on this pi theta. Okay, so now we want to compute the second derivative of the log of the policy. Right? Okay, so I'm skipping a lot of steps. So let's just do that, right? So log of pi theta as. So what is this guy? Right, so in order to compute the second derivative, let's compute the first derivative and then apply another derivative on the first derivative, right? So let's compute the first derivative, the first gradient. So this is pi theta as over gradient theta. Pi theta as. Correct? You know, I'm just applying the chain rule here. Right? And now what is this? Right? On top of it, I'm just going to do another gradient with respect to theta. Okay, so let's use this fact, right? F over G, the gradient of F over G is equals to, it's equal to F prime over G minus G square F times G prime, right? Hopefully you still remember this, you know, this rule, right? For compute the derivative of the ratio F over G. Right, so we're just going to do the same thing here, right? Because we literally are computing the gradient of some ratio, right? Okay, so this is pi theta A over S, right? I do not change my denominator. I'm only going to apply the gradient on the numerator, right? Which gives me second order derivative on my policy. And then the second term is I'm just going to keep the numerator fixed and apply the gradient on the denominator, right? Right? I'm literally applying this rule here, except that I'm doing things here in multivariable rather than a single variable. Right, but the concept is basically the same. I'm just taking derivative on this, you know, the expression looks like F over Q, F over G. Right, nothing's magic, and this expression looks a bit complicated, but nothing's magic, right? I'm just literally following, you know, the basics of calculus. Okay, so let's just put this into this formulation. And this is, what we get, right? And now what I'm going to claim is that this term actually, again, going to go away. This is 0. Right? Why is that? Because expectation sum over A pi theta t as times right? So these two are going to cancel away. And if I pull the Hessian expression outside of the summation, I basically get this, right? What is this? This is Hessian over a constant, which is, of course, 0. Right? Same logic that we did for, proving the baseline is okay and proving, the first derivative is 0 from the previous slides. Okay, so after so much work, and now we get to this expression where we cannot further simplify it. Okay, so we get into this expression where the Hessian basically looks like the expectation of the sort of the outer product of this gradient log likelihood. So this is vector, right, in dimension of theta. So then we get an expression that is a matrix whose dimension is the dimension of the theta times the dimension of the theta. Right? So there's a name for this matrix. This is called the Fisher information matrix. I think this is developed by this Fisher, and I don't really know why they call it the Fisher information matrix, but probably just because of he invented this thing. Okay.
Sorry, what happened to the denominator of pi squared theta t? Like in the expression above, we had that pi squared theta sub t of A given as.
Oh, you mean here?
Yeah.
This
You have
is
derivative of the log, right?
Oh, I see.
It's just chain rule of log. So you have a pi theta.
yeah, sorry, yeah, right, yeah. Yeah, so remember here we have pi theta. So here we have pi theta log, right? Just apply the chain law, like just do this. This is a good question. Actually, when you ask it, I was actually confused as well. So let me just write one more step. Okay. So now we apply chain rule, right? Okay, good. And why this expression is nice? Because we know how to compute the gradient of the log likelihood of our policy, right? Because at this stage, it's just literally like once you implement this policy, you do back propagation on it, you get a gradient as long as your policy is differentiable, right? So this is nice. Once you get gradient, just do outer product between two vectors averaged over samples, you get an unbiased estimate of this Fisher information matrix, right? Okay, so after so much work, we get into this pretty reasonable expression. We basically say that the KO divergence can be approximated by this quadratic function, right? That looks like, penalizing the distance between theta and theta t, weighted by this Fisher information matrix, right? So for now, ignoring about this constant 1 over h, 1 over 2, right? It doesn't really matter that much because at the end of the day, you're going to tune the learning rate. These things just go away anyway. All right, let's put the two Taylor expansion approximation together. We get to this very simple formulation, right? Remember, we did first order Taylor expansion on the objective, and we did second order Taylor expansion on the KO divergence. Right, so we finally, after so much work on calculus, we finally arrived at this very simple formulation where our objective function is linear with respect to the parameter theta, right? Because this is just PG. Right? And our constraint is a quadratic function, right? So this is a positive semi definite matrix, right? Because this is always PSD. Right? So in other words, the matrix XX transpose is always positive definite, right? This is always positive semi-definite matrix. Right? So in other words, my Fisher information matrix is a positive semi-definite matrix, right? Okay, so at this stage, we are pretty happy because this is a simple, quadratic constraint, linear objective function, optimization program. Like we can literally sit down and compute the analytical solution for this program. Right? So this is what we're going to do in the last part of this lecture. And that will give us a very nice algorithm at the end. Okay, so any questions so far for this trust region formulation? All right, so like there are a lot of detailed derivations that we needed to do, and we needed to do a lot of bookkeeping in order to convince ourselves they're correct, right? But the high level is that we were facing a pretty nonlinear, non-convex programming problem. Like we just use our friend, Taylor expansion, right? To simplify this expression, like we do first order Taylor expansion on the objective function, and we realize that it looks very nice in the sense that it's a formulation of policy gradient. And then, we go on to do a second order Taylor expansion on the constraint. And we realize that the zeroth order term is always 0. And surprisingly, the first order term is also 0. And even more surprisingly, the Hessian matrix is actually has a very simple expression, right? It's the Fisher information matrix, expectation over SA of the log likelihood. Okay? And it is always a PSD matrix. Okay, that's basically what we did. Okay, so remember the high level goal, and the rest, you can actually just sit down and do it on a paper. I think everyone should be capable of doing that, right? Because at the end of the day, it's basic fundamental calculus. All right, so let's look at this expression, right? So what I'm going to tell you is that you can solve it exactly. And indeed, this gives us this nice expression. So you just apply the matrix inverse on this Fisher information matrix, and then then multiply it by the gradient. Right, so here, let's just assume this guy is invertible. If not, we're going to use pseudo inverse. Okay, but let's just for simplicity assuming this is invertible. And in practice, if it's not invertible, you add a regularization. So maybe you will do this. Okay. Lambda is maybe 1e-7 or something. You add a regularization to make it invertible. Okay. And if you don't like regularization, just take pseudo inverse. That's okay too. Okay, so that's the expression that we will get if you solve this maximization problem. And even nicer is that you can analytically compute the gradient step size eta. So the gradient step size eta will be a function that depends on your trust region size delta, right? So delta will show up here, and your denominator will depend on this like inner product between the gradient, Fisher information matrix inverse, and the gradient. Okay, so at this stage, you please trust me that this is the solution. This is the optimal solution for this linear objective function quadratic constraint optimization problem, right? And I'm not going to talk about how we derive this here, because I wanted you to actually think about it offline. So on Tuesday, let's just do a quick recap. And when we do recap, let's just derive this formulation. Right? Okay, so let's just put that into an algorithm framework. So let's initialize theta 0. And then for t equal to 0 all the way to some point when we get converged. Every time step, let's first estimate the policy gradient, right? here I use the word estimate because I wanted you to think about the situation where we use like finite number of samples to approximate the gradient, right? We can get an unbiased estimate of the gradient. And then let's estimate the Fisher information matrix, right? Again, we estimate because we need to replace this by finite number of samples. Right? So that we can do that. We know how to draw samples from a distribution, right? Right, let's just do natural gradient descent. Okay, so this formulation is actually called a natural gradient. Right, so think about this as something like, a preconditioned gradient. You have the gradient, so instead of following the gradient, you first precondition it using this matrix inverse. Right, and then you follow this conditioned direction. Okay, so you're going to use this analytical expression of eta. So this is pretty nice in the sense that instead of tuning the learning rate, which really doesn't have that much like meaning, right? Like we should tune the trust region because that has some meaning, right? Because this is saying like this is the KO divergence between two distributions, right? Like if you just tune in learning rate inside the parameter space, that doesn't really tell us anything because like parameter space, you can scale it, you can rotate it, you can just like apply any linear transformation, right? But like the trust region is kind of well defined because this is a KO divergence between two distributions, right? So we're gonna tune this delta rather than tune eta. Right. So that actually will make your life much easier when you implement NPG and tuning hyperparameters. Of course, in your homework, TA has already tuned the delta for you, but you will see that the delta that the TA picked is a very common number. It's like 1e-2. Right. So you're always going to start things like 1e-1, 1e-2, 1e-3, something like this, right? But like you pick a number, it just works. This is much easier than tuning this parameter. Right, you can try it out in the homework. Right, we're gonna just implement this in a very general way, and we're gonna test it on a couple. But you can actually test it on other environments as well. Okay, and you will see that actually, if your implementation is correct, you will actually see it learns pretty fast. Like you repeat this process for like 20 iterations, it pretty much learned the policy that solves this problem. Right, so the number 20 is actually important. You can use that to check if your implementation is actually reasonable.
Professor, what are the limitations on this kind of estimation? Because we are estimating the cost and like the A pi theta t s comma a as well as the KL divergence. So is there like a limitation on where this works and where this doesn't work?
Yeah, I mean, so how many number of samples you use to estimate the gradient and how many number of samples you use to estimate the Fisher information matrix is also another hyperparameter, right? So this is the size of the mini batch. So you want to always striving for a balance between the number of samples you used to estimate these quantities and also the accuracy, right? Like ideally, you want to use infinitely many samples.
No, that's all. So what I was asking is basically with regards to, is there like a limit, like are there any limitations onto what kind of problems this can be used on, like like with particular rewards or anything like that, or in general, can this be a policy that is used like everywhere?
It's general.
Okay.
So this is literally, one of the state of arts. Right. Right, so that's all I want to cover. So let's just do a quick summary. All right, so we talked about trust region policy optimization, and it's motivated from conservative policy iteration, right? So we said that, at iteration T, let's try to find the maximum local, the policy that maximizes the local advantage against the current policy, subject to a KO constraint, right? So in other words, we want to be greedy, but simultaneously we want to be incremental when we update, right? Incremental here means the KO divergence is not too big, right? then we say basically, this looks very complicated. The objective function is nonlinear, non-convex. The KO divergence is even more terrible because we don't even know how to implement the likelihood function, right? Because the transition is unknown. So what we said is that let's just apply first order Taylor expansion on the objective function and then second order Taylor expansion on the constraint. All right, and surprisingly, a nice thing happened. What we get is a pretty nice linear objective function where the gradient is essentially the policy gradient, right, which we know how to compute at this moment. And even more surprisingly, we see that after we applying second order Taylor expansion on the KO divergence, the complicated non-symmetric KO divergence actually is reduced to this symmetric quadratic formulation, right? So this is symmetric. While KO is not symmetric, right? So in other words, KO up to second order, it's symmetric. Right? The asymmetric stuff actually is coming from the third order, fourth order, fifth order, higher order polynomials. Right? So we should be happy at this stage, even though we still need to do some work to get the closed form solution, but we should be happy at this stage because our objective function is linear, our constraint is quadratic. So this is a well-behaved convex optimization problem, right? And even nicer, the constraint is a quadratic constraint. So that should convince us that we can compute the analytical solution for this program. So I leave this as an exercise, and we're going to talk about it next Tuesday. Right? And after we do this optimization, we get to this very nice formulation, which is called the natural policy gradient. Right? So this is the natural gradient. So natural gradient is actually a thing. Okay, so it's not, if you Google natural gradient, you will actually see similar expression where you have a gradient and you precondition the gradient by Fisher information matrix, the inverse of Fisher information matrix. Right? So this is called natural gradient. So the reason that we call it natural policy gradient because we are applying this thing in reinforcement, right, on policy. So that's why they call it natural policy gradient. Okay, so that's the algorithm. And then now you actually just repeat, right, until you converge. Right, so that's all I want to cover today.